So in the morning we saw, the analysis for V less than 0, okay, and then we finally related the charge in the semiconductor to the voltage in the voltage applied across the junction. And then what is the charge on the metal? Qm charge on the metal. So this will be equal to Qs because there is no charge earlier in the device. So when we put V less than 0, some charge appeared in the device. We denoted it as Qs for charge inside semiconductor. So there is an equivalent charge appearing on the metal. So that should be equal to negative of the semiconductor charge. Okay, it should compensate, right? So here there's a small mistake I made. So here this electric field is not continuous here because the epsilon is different, right? Epsilon oxide and epsilon semiconductor, they're different. Epsilon oxide is 1/3 of epsilon semiconductor. Since normal displacement vector should be continuous, so since epsilon is smaller here, electric field should be more here because epsilon ox Eox should be equal to epsilon silicon and times electric field inside silicon. So this should satisfy across the boundary. So it will not be like this. So slight variation. So it will be small. So like this, I should not show it like a continuous curve. So there should be some discontinuity here in the electric field. But what we have said about negligible area under the curve and all is valid. Just that I should not draw it continuous. So having rectified this, let's move on. So this is afternoon class. So we now have to carry out analysis for V greater than 0. So this is the biasing MOS M and then an M to the right side, V greater than 0. So for V greater than 0, we should have positive charge on the metal because V greater than 0. So terminal, positive terminal. So positive charge should go to metal. And there should be negative charge in the towards the negative terminal. And we said that there cannot be charge here because there can be free flow of charge between metal and semiconductor, so it cannot stay here. So it will come till the negative charge will come till semiconductor surface. I mean semiconductor oxide interface, which in other words surface we call it sometimes. And then it stops there because it cannot cross. In case it crosses, then it's just a current flow, right? So it cannot cross because there is an oxide. So negative charge can come from electrons or ionized acceptors. So there should be a negative charge in the semiconductor near the surface. And in a semiconductor which is p-doped, negative charge can come from only electrons and ionized acceptors. So let us see how the picture will look like for carrier concentration as we increase voltage beyond 0 volts. So first, hello, yeah, any doubt? I heard somebody saying something in between. Okay, so V1 0. So this profiles, I'm going to draw multiple profiles. So in front of you, I wanted to draw. So that's the reason I left the left blank here, left things blank. So this one indicates, and then the solid line indicates PP naught. So which is hole concentration for voltage equal to 0. And then the corresponding electron concentration is constant, which is at NP naught. So there is no charge for V equal to 0. And for V2, say voltage V2, which is greater than 0. Okay. So what will happen? Negative charge should come in the semiconductor. That can come from electrons and then ionized acceptors. So electron concentration will electron concentration will change like this. And correspondingly, because Ni equal to Ni square, Pn equal to Ni square has to be satisfied because MOS junction is under equilibrium even when bias is applied. So hole concentration would do something like this. so that P into N equal to Ni square. So hole concentration goes down, thereby exposing ionized acceptors. So there will be negative charge because of uncompensated ionized acceptors, because hole concentration has come down and electron concentration has gone up, and thus creating some more negative charge. So this is how negative charge comes, by electron, but by increasing the electron concentration and by reducing hole concentration, thereby exposing background ionized acceptors. So this is say 2. Okay. Now case 3 is, for which case 3, that is V3 greater than V2. So we are increasing the voltage further beyond V2. And in that case, Ns and Ps are equal to Ni. So this S stands for surface. So Ns and Ps means concentration at the surface. So means this concentration. So here it is Pp naught for V equal to 0, and it is less than Pp naught for V greater than 0. That is equal to V2. So for V3 greater than V2, then there will be further increase of concentration of electrons like this, and there will be decrease in concentration of holes like this. All right. So this is case 3. Okay. So in this case, NSPS are equal to Ni. So this is the dotted line is Ni. So PP naught, I mean from PP naught, hole concentration has come down to PS, surface hole concentration PS, which is equal to Ni. Similarly, electron concentration has gone up, and at the surface it is equal to Ni. So Ns and Ps are Ni. Now if you increase voltage further, what happens? Hole concentration would go down further, electron concentration would increase further. So how will that look? It will look like this. So here maybe I will just extend for some more region. Here don't think I'm drawing PP naught and all in metal, okay? So this diagram is independent of this, you can think of, they're not like related for the same X. So now hole concentration should be, from here it should fall, and it should be this one. So something like this. So this is say 4, 4. Yeah. So so for V equal to V4, which is greater than V3, Ns is equal to Pp naught. So this is N is increasing towards the surface. So at surface, the electron concentration is equal to Pp naught. And at the surface, the whole concentration is equal to Np naught, because if electron concentration is Pp naught, whole concentration has to be Np naught, because Pp naught Np naught gives you Ni square, which is what we should have in deep inside. Here Pp naught and N naught multiplying together, you will get Ni square. So this is how it is. And if you draw the carrier concentration in linear scale, how they look is also what is of interest to us, because this linear scale gives us some better understanding of how to make approximations always. Okay, so drawing things in logarithmic scale and linear scale are very important, because this linear scale sometimes throws you very nice what do you call approximations that you can make. So let us draw for first one. So this is Pp naught. So 1 means no charge. So if the whole concentration is flat. For 2, condition 2, V is just greater than V, 0. So whole concentration comes down. So how much comes down depends on the strength of V2. So so let us say it has come down slowly like this. So I should start here. Start here means I should drop it quite quickly, because you know that concentration rapidly falls, okay, in debye length, in the range of debye length. And then this is 2, this is 1, and then 3 means I should start from here. So this I should start like this, and then I should start from here. So this is where electron hole concentration started coming down. Remember, note that we cannot draw electron concentration in the same curve unless electron concentration becomes significant. So this is 3. So 3, what is 3 means, it is like it starts from 0 like this. Maybe for with a different color I'll show, so that, so this is V2, right? So this is what I meant. And this is V3. So hole concentration is almost appearing 0, and then increasing rapidly, and then merging. So this is how it look. So V4 will look like what? So here I have here, right? So up to here. So I should, I'll have 0, almost it shows like 0 for a very long distance, then increases and becomes P naught, PP naught. So this is how it looks. What about electron concentration? Electron concentration will not appear for 1, 2, 3 at all, because 1, 2, 3 it is still Ni. Up to 3 it is still Ni. Electron concentration is less than or equal to Ni. You cannot show anything of the order of Ni when you plot in linear scale, when PP naught is of the order of 10 power 15, 16, 17 or so. So what you can show is only for the case of 4. That is because electron concentration has reached PP naught at surface. So the electron concentration you can show only for, okay, so this one is for 4. So this is for 4. So for 4 you can show actually electron concentration also. So how will you show for 4 electron concentration? It starts at PP naught, and then it quickly goes down to 0 like this. Okay. So this is what is electron concentration here. So this is nothing but electron concentration. Rest all are hole concentration. Okay, this is hole concentration. So rest all are hole concentration. Only this particular curve is electron concentration. Okay, so this is how it look. Okay, so it is you see that there is a depletion of holes. Okay, so when it is V is up to V2 or V3 or even up to V4, there is depletion of holes over certain distance. Okay, because holes are small. This is how you have seen in the PN junction case. If you plotted hole concentration, electron concentration in the linear scale, then at the junction region you would see hole concentration going down to 0 like this near the junction. So that is basically indicating depletion of holes. So for the case of 2, 3, and 4, we have depletion of holes. And especially for the case of 4, in addition to depletion of holes, we have something called electron piling up here, okay, at the surface. So this kind of thing is called inversion. So at this voltage V4, when Ns is equal to PP naught, the semiconductor is said to be inverted. So inverted means what? Inverted from what? Inverted from P to N type. So until some small voltages, the surface concentration of electrons is less than hole concentration. So at the surface also, it is still acting like a P-type semiconductor. But the moment is more than p-type concentration, then it is like acting like what? N-type semiconductor. Just that there is a background concentration of acceptors, but that is immaterial because we have electrons in majority, so it acts like N-type semiconductor. So that is what we call here. So Ns is greater than P, much greater than Ps. So actually, if you see, it is not only for V4 when Ns is equal to Pp naught, surface concentration is equal to hole concentration deep inside the semiconductor. You see that inversion starts for V greater than V3. What did we say about inversion? Inversion means inverted from P to N, means electron concentration should be higher than hole concentration. So if you see V3 itself, you see that at surface electron and hole concentrations are equal to Ni. So the case of V3, so we see that the surface concentrations are same, equal to Ni. And if you increase voltage beyond this 3, then electron concentration will increase and hole concentration will decrease. So beyond V3 itself, you start seeing inversion. Okay, so inversion starts for V greater than V3 when Ns is greater than Ps. However, we do not see much electron concentration at the surface for V slightly greater than V3, as can be seen here in this plot. In the linear scale, if you plot, even for the case of 3, you don't see electron concentration much because that is still in the order of Ni. Okay, so that is why we don't usually call it as strong inversion as inversion. So just to have better words, what we can say is for V greater than V4, the electron concentration is significant, and we talk about inversion and we call it strong inversion because we don't want to confuse people saying inversion means only V greater than V4, etc. Okay, even V greater than V3 also there is inversion. So what we say is, okay, fine, V greater than V4, let us call it strong inversion. So strong means very strong concentration of electrons, you can say. Okay, and for V3 to V4, for voltage between V3 and V4, let us call it weak inversion because electron concentration is still weak. Okay, that's what we meant. So if you just see different regions, 0 up to V4 only we considered. What happens if V is still greater than V4? We will come to that little later. Okay, so for now let us understand things between 0 and V4. So 0 to V4, well, voltage is varying and it is called depletion regime because Ps is less than Pp naught. So throughout this voltage range, P is always less than Pp naught. So depletion of carriers, depletion of holes, majority carriers. So it is depletion regime. It is, this region is called depletion regime of operation when voltage is between 0 to V4. But this actually has a part, right, which is V3 to V4. So there is a subpart of this 0 to V4, and that is V3 to V4, and we call it weak inversion regime. Okay, so which is part of depletion regime actually. So this is what I have written here. It is called part of depletion. So weak inversion regime is actually part of depletion regime. Okay, so just that electron concentration is something like this between Ni and Pp naught. And greater than V4, anyway, we call it strong inversion regime because Ns is greater than Pp naught. And note that depletion of majority carriers is still there. So it is called depletion regime, and we have a new name for V greater than V4, calling it strong inversion and not depletion, because minority carriers, which were electrons earlier, now have become majority at the surface. So very high concentration of electrons has come. Okay, for that reason, we want to not say simply depletion because it is not depletion of both carriers. Okay, there is only depletion of one carrier, that is hole. Okay, now we cannot say depletion of electrons because electrons are very strong in number now, very large in number. So that is the reason we coined this word strong inversion. But that doesn't mean there is no depletion at all. Depletion is still there, but what kind of depletion? It is depletion of only one carrier type, that is depletion of majority carriers. Okay, so any doubts so far? Is it clear? Okay, I'll move. Yeah, I'll move forward. So there is this voltage axis, just repetition. So there is this electron concentration axis, surface electron concentration, NS, on log scale. And this is voltage axis, linear scale. This is linear scale. So you see that at V equal to 0, surface concentration is NP naught. That is the concentration deep inside semiconductor, same. So no band bending, etc. So, and at V3 you have Ni, and at V4 we have Vp naught. So we saw earlier that less than V0. So this is called accumulation. We have seen accumulation means accumulation of majority carriers, that is holes. And V0 to V4, that is called depletion regime. And in that depletion regime, there is a part that is called weak inversion, that is between V3, V4. And beyond this depletion regime, that is beyond this V4, it is strong inversion. Okay. And if you see, there are names given for these voltages. What are the intermediate voltage? For a preliminary course like this, introductory course, we will not assign a name for this. So we assign the name something like VFB for this voltage, and for this voltage V4 we assign a notation like VT. So what are these? So, and then we, in this course, whenever we say inversion, we mean strong inversion, because weak inversion is somewhat complicated, and that is not part of first level course. So we treat only strong inversion. Weak inversion we will not treat in this first level course. So we have only two, just for understanding, we have put, we have made it clear now here, but we will not deal with the weak inversion. We treat it only like three regions of operation, which is accumulation, depletion, inversion, strong inversion, which is just inversion for our course. So this one, then in that case, you have only two limits, voltage limits. So that is VFB and V4, VT. So that is what is this. So this is accumulation. We have only three regions. So accumulation, depletion, inversion. Inversion means strong inversion for this course. So so this VFB is called. So this VFB is called flat band voltage. Okay. So flat bands in semiconductor means no charge in semiconductor. Okay. So this flat band means bands are flat. Okay. So the equivalent picture in terms of charges, there is no charge. All right. So this is called threshold voltage. Why it is called threshold voltage, we will understand it when we talk about IV characteristics of transistor. So threshold voltage, we call it, or even when we really go into plotting CV characteristics. So two voltages, three regions of operation, two limits, flat band voltage, threshold voltage, and let us derive equations for it. And VFB equal to 0 for an ideal MOS junction. And what is VT now? That is what we have to derive. So rest of this lecture, we will derive an expression for VT. So little math and physics. So MOSM. So this is how we have. And earlier we have seen for VT is what we are going to derive. So we are going to consider profile 4. So this is hole concentration, and this is electron concentration. Okay, so hole concentration goes like this, and electron concentration starts at PP naught, goes like this. Okay, so we are interested in this VT. So for this picture, let us calculate the applied bias. What should be the so it is like reverse working. We know that this is what we call it as threshold voltage, and this is how the charge profile looks like. And if you find the potential drop, that should be the voltage that we should apply. So it is like working reverse way. Okay. So now from this, how do we get voltage? As we have seen in the morning class, first we should connect charge to electric field and electric field to potential voltage drop. So this is concentration. Charge picture comes from concentration picture. So that is there anyway here. So from here we should go to charge picture. From concentration picture we should go to charge picture. So charge is going to be negative. So I will draw x-axis little on top, and this is basically space charge density rho, and rho is nothing but q times p minus n minus na. So p is almost a 0. So because in this region p is almost 0, and in this region it is neutral. So wherever space charge is there, p can be negligible. So p is much less than n plus na, implies rho is equal to q times n plus na with a minus sign. So when n is much smaller than na, okay, so rho is almost equal to q minus qna. So this depletion of holes corresponds to depletion, I mean na minus charge. So there is na minus charge like this. So this is how Na minus charge will be there. On top of this, I have to add electron concentration. So minus Q times N plus Na. If you ignore this N, I mean, if you keep this N aside, it will be minus QNA. So this is minus QNA. Okay, but there is electron concentration also. I have to add that. And electron concentration, if you see, that is this is in linear scale. Okay, electron concentration, if you see, this is minus qna, right? Here it is minus q, here it is equal to na, because pp naught is na, pp naught is na. So electron concentration at this plus surface is na. So you should have 2 times this minus qna, because electron concentration is also n, and it is decaying rapidly. So actual space charge looks like this. So this I will just erase. So this is how it will look. So actual space charge profile. So because beyond this point, electron concentration is 0, like this, it is decaying. So if you add this and this, you will get only this curve for most of the regions. Okay, only towards the surface, electron concentration counts. So only up to this region, electron concentration counts. Say in that region, we have added. Okay, it is 0 from 0 to Na, and here is where we have added 0 to Na here. So this is minus 2q Na, say. Now what is of importance is, what is the and if the next thing is plotting electric field. We know that an equivalent positive charge comes on the metal, and that will be a kind of impulse function here, positive charge. So we are not analyzing here the charge picture in the metal, because the voltage drop in the metal also will be 0. So what we need is voltage drop in the oxide and voltage drop in the semiconductor, or what are going to decide the total voltage. So now what happens is, now we have to find electric field. So it is a negative charge here. So I will draw x-axis little below, so that electric field can be drawn on top, because this negative charge, positive charge here, field should be in the positive direction. Okay, now I will see what electric field can be. So earlier we have seen, if this is metal, this is oxide, this is semiconductor. Okay, metal, oxide, semiconductor. Then if you take a Gaussian pillbox like this, we have seen earlier that E or epsilon ox should be minus Qs by T ox. This is what we have seen earlier, in the morning class. Epsilon ox T ox equal to, epsilon ox E ox should be equal to with a minus sign, because electric field direction is this. We have seen in the morning class this derivation. So epsilon ox is minus Qs by E ox is electric field in oxide, it should be equal to minus Qs by epsilon ox. But what is Qs? What is Qs? Qs is charge inside semiconductor. So that is nothing but integration of rho times dx. Okay, integration of rho times dx gives you charge. So that is area under rho versus x. All right. Now here is where we make approximation. So this is what the area is what we want. Okay, this is the total area. So this is the total area is what we want. Okay, so here is where we make some approximation. First approximation is depletion approximation. That is like making this really sharp because it is transitioning slowly. So let us make this sharp. So what I'll have, I will plot rho here for the approximation. So rho approximate. I should not say rho approximation. So actually rho used for approximating Q, because it is not that we are approximating rho. Remember that. Okay, rho used for approximation of QS. Okay, remember we are approximating area. We are not approximating rho, because what we want is QS, which is integral of rho dx. It is not that we need to have approximation on rho. It is sufficient if we can make approximation on integral rho dx itself. So there is some charge here, tail. There is charge decay here. So put that charge here, which means you make this sharp. So that excess charge, you just push it inside, which will yield you the same charge amount of charge. All right. Now the profile is something like this. It will look like this. So this sharp transition is called depletion approximation. Okay. And now if you see, this is the total area. In this total area, what I say is, this is the area just coming from minus QNA. Okay. So this area is due to minus QNA times rho, right? So this is minus QNA. This area is coming from minus QNA because this is minus QNA. So there is this small area which is coming from electrons. So that is this area. Okay. So this area is coming from electrons. Area coming from Na. Okay, so area is coming from electrons. So what you can say is, you can say that area approximation here, area contribution from electrons is much smaller than area contribution from Na minus. So what I am saying is rho dx equal to rho times q minus q times n plus Na dx. I am approximating this to minus q minus qna dx is xd. Okay, so xd is, this is xd. Okay, so or in other words, I am approximating this to be that electron concentration will be from when you calculate area, it will be okay. In other words, actually correct way of writing this is not neglecting n. what you should do is, this is where you should write like this. And now I can say that this is much smaller compared to the other term. Okay, so implies integral rho dx is equal to minus qna xd, where xd is the depletion width, I can say. Okay, so xd is the depletion width. So this is the picture I have for rho. So with this, what is qs? So implies qs is equal to minus qna xd. So this is my qs. Okay, now, and what is xd? I don't know what is xd, right? So xd, how you calculate? You know that. Okay, we will come to that later. Okay, so let us find from rho, we have to find electric field, right? So electric field will be like this. So when rho is constant, you know that electric field comes from dE by dx equal to rho by epsilon. Yes. So from here, electric field starts. Okay. Negative charge, so it falls rather. And then for most of the region, rho is flat. So in this flat, rho slope should be constant here. So which means almost up to this region, I should have E constant like this. Sorry, E linear. Okay. So in this linear, it is E is linear because rho is constant. And for end, it is going to 0 here when rho is going to 0. Rho is much negative, so electric field slope should be negative and it should vary. So it should be something like this. Okay, so it should be something like this. Then there should be epsilon ox also, oxide, because if this is epsilon, this is ES, electric field at the surface, then this is electric field inside oxide, and epsilon ox and epsilon s, e ox and es, they should be related by epsilon ox times e ox should be equal to epsilon s times es. Since epsilon s is more than epsilon ox, e ox should be more than es. All right, so this is what e ox will be like. And now the area of this gives you total voltage. Okay, now let us do that to get threshold voltage Vt. So here also we make some approximation. So let us plot this electric field. Let us plot this electric field and try to obtain integration. So epsilon ox, what all things we need? Qs we know, but xd is not known. Epsilon x in terms of qs we know formula. Okay, but we have to integrate this area. So there is this area which is easier because epsilon E ox is constant. Why? Because rho is 0, which means electric field slope should be 0. Rho is 0 inside oxide, it is insulator. Okay, so this area, and then there is this area. Okay. So the approximation here is, so here it is almost like a triangle except for a very small portion here. Okay. So here is where we make approximation again, that this curved region can be neglected and it can be made, made really triangular. So the approximation here for electric field, it is not exactly for electric field. Again, it is for, frankly speaking, it is for voltage, calculation of voltage drop. But we will just consider the same thing like how we drew for rho. So the approximation is something like make it triangle. Let me know when you see the screen. Just somehow, can you see it?
Yes, sir.
Yeah. So the approximation here is approximate this region to be a triangular region. That's all. Okay. So we know why this is a triangular shape. Why? Because rho is constant, equal to a QNA minus QNA throughout. So slope is negative, and it is slope is constant. So E is varying linearly. Understood. So why this is flat here? We have seen it in the morning. Rho is 0 here. So slope should be 0. So electric field is constant. So metal, inside metal, we are not drawing electric field because they decay very rapidly and they don't contribute to significant voltage drop. So we are plotting electric field only in oxide and semiconductor. So the approximation here is it is that it is epsilon ox here, and it is proper triangle here, perfect triangle. Okay, so and this is epsilon es, and this is eox, and this is xd, and this is tox. Okay, so this is xd in the sense this distance is xd. You can treat like this to be x equal to 0. You can treat, so which means this becomes x equal to xd. This becomes this is basically thickness tox. All right, now we have to integrate this, right? But we still don't know what is xd and what is es epsilon ox. We have to see. Earlier we have seen that it is Gaussian pillbox. If you take metal oxide semiconductor, Gaussian pillbox, if you take between one surface in oxide, one surface in semiconductor, you have related epsilon ox as minus q by minus qs by epsilon ox, eox equal to minus qs by epsilon ox. But if you want es, either you can just use that continuity relation, continuity of displacement vector, or you can use the Gaussian surface to be aligning with this semiconductor surface, in which case you will have epsilon s entirely, it is in semiconductor, entire Gaussian cylinder, but the left surface of the cylinder is exactly at the interface. So this will be equal to minus qs by epsilon s. That's all. Okay, just everything else remains the same. If you have it here for the surface, you will have it as epsilon ox times tox gives you minus qs. Okay, so here if you have epsilon s, es gives you minus qs. Okay, so that's why these both are equal, which is nothing but satisfying the displacement vector continuity across a boundary. All right, so that is how we know what is es, what is epsilon ox. So the only thing remaining is what is xd, because qs is in terms of xd. Then we can just find out, integrate electric field, and then find out voltage drop. So how do you find xd? Already it is known for you because you have done it in the in the PN junction case. All right. In the PN junction case, we have drawn. All right. So I'm not going to, do it to a great extent, but just cover it up. So how will you get XD here? This voltage drop in the semiconductor, voltage drop in the semiconductor, I call it psi S. So let us introduce some symbols. Voltage, potential difference, I would say. Potential difference across semiconductor. Okay. And then psi ox, I call it potential difference across oxide. Okay. Now, so let us take psi S. Psi S equal to Vt ln. You know this from Boltzmann relation. When Vt ln ns by np naught. Okay. This is from Boltzmann relation. You know, right? When things are in equilibrium, Boltzmann relation, because MOS junction is in equilibrium. Okay, we have seen PN junction also, Vt ln Na Nd by Ni square, all that is coming from Boltzmann relation only. So similarly, if you have a concentration variation for electrons like this, the potential drop will be in this direction, because from increasing electron concentration to decreasing electron concentration, and this is psi S, that is given by concentration at the surface Ns, concentration inside, that is Np naught. If you want to relate in terms of holes, it will be like this. It is Pp naught here, and hole concentration comes down, and what you should use is Pp naught comes on numerator and Ps comes in the denominator for holes. That is, you know that how it comes. So Vt ln Ns by Np naught. So this is known. Okay, so this is equal to Vt ln Ns is what? Pp naught. Okay, because Ns equal to Pp naught for V equal to Vt. That is the definition. Okay, so we get this. Now we have Np naught as Ni square by Pp naught. So 2 times Vt, sorry, I'm going fast, ln Pp naught by Ni square by Pp naught, because Np naught is Ni square by Pp naught. So that means Vt ln Pp naught square by Ni square implies psi S equal to 2 Vt ln Pp naught by Ni. Okay. So this is semiconductor charge potential difference, and this must be equal to area under the triangle, half times epsilon S times xd. Okay, this is the area under the triangle, half times height into base. Height is epsilon x ex es, xd is the depletion width. I will finish it in 10 minutes, this derivation, so please bear with me. So half times epsilon s is already known. What is this? Es, sorry, I'm just using epsilon very often. Es is minus qs by epsilon s. Okay, and this is xd, and qs is minus qna xd. We have seen that, so it will be qna xd by epsilon s into xd. So you will have xd square, implies xd equal to 2 epsilon s psi s by qna under square root. Why? Because 2 epsilon s psi s 2 epsilon s goes this side, 2 epsilon s psi s, and QNA xd square is there. So xd is there. So you will get root of 2 epsilon s psi s by QNA. Now we have got xd also. We have got psi s from Boltzmann relation. This is already known. There is nothing that is unknown. PP naught we know, which is nothing but Na. Okay. So this is known. XD also is now obtained. Now ES also is known. Epsilon EOX also is known. Now the total potential drop is what we have to find out. And anyway, the potential drop inside semiconductor is psi s is already derived. So what we need is psiox. Okay. Psiox is what? This is nothing but simply integration of EOX, EOX. So that is EOX dx integral. That is nothing but EOX times TOX. It is rectangular shape, if you recall. So this is rectangular shape. Area is simply EOX times TOX. So this is equal to EOX is again minus QS by epsilon ox into TOX. You note that epsilon ox by TOX, what we have identified it as? We have identified it as COX. So minus QS by COX. So that implies psiox is minus QS by COX. Okay. So let us write all the equations together. Now we have found what is Vt now. So Vt equal to psi ox plus psi s. Okay, I'll write in the next page. Vt equal to psi ox plus psi s, because that is what is applied voltage. All right. So ideal MOS capacitor we are considering. So this is for ideal MOS cap. Let us write it, because things will change. This expression will change if it is non-ideal. So Vt is equal to psi ox plus psi s for ideal MOS junction, because that is the voltage we saw. Nowhere else voltage drop is there. And this is the first equation. Psi ox is minus QS by Cox. Is Cox, you know, and then this psi s is nothing but 2Vt ln PP naught by Ni. So psi s is known. So QS is what you need. QS is minus Q Na XD. And so XD is needed. So XD is square root of 2 epsilon s psi s by Q Na. So everything is obtained now. Vt means ideal MOS junction, means this is what is Vt. Psiox is minus QS by Cox. And QS is minus QNA XD, where XD is this. This is something like a depletion width formula that you have derived in PN junction case, square root of 2 epsilon s by QNA. Instead of V built in, you have psi s here. And psi s is nothing but semiconductor potential drop, which is coming from Boltzmann relation. Okay. So this is what it is. And sometimes this is called 2 times phi f. Okay. Where phi f is equal to Vt ln PP naught by Ni. So what is this phi f? Why it is called phi and with a subscript f? This f stands for Fermi level actually. So if you have EC like this and EV like this, and this is EI, and if p-type semiconductor means EF. So clearly, if you see PP naught by Ni, so this is basically how much P it is with respect to intrinsic. So how much EF, where EF is with respect to EI. So this tells you what, how strong P it is with respect to Ni. That is what that is what is coming by ln PP naught by Ni. So in other words, how strong it is P with respect to intrinsic Fermi level. So we have seen earlier. So this is nothing but Q times phi f. So that is why the subscript f is used. So it is basically difference between Fermi level and EI. Okay, so given a p-type semiconductor, your phi f is fixed because you have fixed concentration of holes. So you have fixed Fermi level. So you have done this. There is some noise. Okay, so with this we have derived threshold voltage expression. Okay, so we psi s is 2 phi f. So here you can say, here it is, if you put 2 epsilon s, I will not write because there is a point in not writing here. Okay, this is only for threshold voltage. Okay. Just a second, let me just recollect if anything is missing from threshold voltage is over. So yeah, let us write this QS. So this is basically what earlier also we saw same relation, right? So oxide drop across oxide is simply given by a charge on either whichever side you take, either on metal side or semiconductor side, you take total charge by capacitance of the oxide. So as far as oxide is concerned, just that oxide is acting like a capacitor. Okay, so the drop across that oxide is always given by this charge on the plates by Cox. Charge on the metal is varying rapidly, so potential drop is 0 in the metal. But charge in the semiconductor, it was varying rapidly, and then integration of that electric field has become 0. We have neglected the drop across semiconductor in case of accumulation, but in case of depletion and inversion, we cannot neglect, because you've seen that this electric field is comparable to this electric field, or this area is comparable to this area in case of depletion or inversion. So unlike in case of accumulation, where the electric field area in the semiconductor was neglected. So that is what is one difference. So that is getting added. Okay, so here, that is why we have psi ox plus psi s also. All right, so if you yeah, that's all. So we'll solve, time is not there. I thought of solving a small example, but we will meet in tomorrow's class and then solve an example for this, and then discuss the case for V greater than V4. So V greater than VT, what happens? All right, with that, and then we will conclude, try to conclude the CV characteristics also if possible. Okay, so I'm closing the meeting if there are no doubts. Any doubts? Okay, I'll close the meeting.